Flow is the process variable which, when controlled, maintains other process conditions, such as the pressure, level, and temperature values required to keep plant production and quality at the desired level. Although flow is the most frequently measured of all the process variables, it is one of the most difficult measurements to make accurately. One of the basic premises of fluid mechanics is that mass is a conserved quantity. The mass entering a system is equal to the mass leaving the system when both are measured over the same time interval. The simplest method for determining the rate of flow of a fluid would be to catch the fluid in a container and weigh it over a given interval of time. It is not always possible, however, to determine flow rate by weighing the fluid. An example is gases that cannot ordinarily be condensed into a liquid, or in cases where you cannot break into the system to make weight measurements, such as a closed-loop chemical process. So it's clear that the basic weight per unit of time method must be augmented by other, better-suited means. In this program, we'll be taking a look at the different methods and devices used to measure flow. But before we discuss flow measurement methods and devices, let's review some basic concepts regarding fluid properties and their effect on flow. Let's begin by looking at density. The Greek letter rho is conventionally used as a symbol for density. Density is the mass per unit of volume. Basically, density is how close or tightly packed the molecules that make up a substance are to each other. Expressions of density are typically stated in terms of pounds per cubic foot. Density is a property of all substances, and often a distinctive one. Because of density, the same volume of different substances is likely to be different in weight. The effect of density on weight is shown by this illustration of a cubic foot of iron and a cubic foot of water on a balance scale. Because the iron has greater density, it weighs more than water. The relationship of density to weight applies to all matter, whether it's solid, liquid, or gas. The density of mass will also be affected by temperature and pressure, but the effects of these two factors vary for different physical states. Let's look at what happens to the density of a substance when its temperature increases. The substance expands when heated. This means that its volume increases. Now, if we take this information and the density formula, we can see that as the volume of a substance increases, while its mass remains constant, then density must decrease. The reverse is true if the temperature decreases. As the substance cools, it contracts. This means that its volume decreases. Again, using the density formula, we can see that if volume decreases, but mass remains constant, density must increase. So, generally, an increase in the temperature of a substance decreases its density, and a decrease in the temperature increases its density. Temperature will usually affect the density of solids, gases, and liquids differently. Solids are least affected by changes in temperature, while the density of gases are affected the most. Liquids fall in between solids and gases with regard to the effect of temperature on density. Pressure can also affect the density of a substance. When the pressure of a substance is increased, the substance will compress. But when the pressure is reduced, the substance will expand. Let's use the density formula again to see how pressure affects the density of a substance. As pressure increases, the substance is compressed and its volume gets smaller. So if volume decreases because of an increase of pressure and mass remains constant, then density must increase. By the same token, if the pressure is decreased, the substance will expand. So if volume increases but mass is held constant, then density must decrease. Usually, the effective pressure on the density of solids and liquids is so small that it can generally be ignored. However, its effect on the density of gas is very pronounced, and it is a factor that must be considered when designing systems to measure the flow of gases. Another term that's commonly used to express the density of fluids is specific gravity. Specific gravity is simply a ratio that compares the density of a fluid at a specific temperature to the density of either water or air at the same temperature. The resulting value is dimensionless. That is, it has no units associated with it. It is this quality that makes the specific gravity of a fluid so useful, since it can be used as a factor in combination with measurements in any unit. So far in this program, we've seen that density is the mass of a substance within a unit volume. That density is affected by temperature and pressure, and we've discussed how specific gravity is used to relate the density of fluids to water or air. In the next section, we'll focus on viscosity, another property of fluids that affects flow measurement. In this segment, we're going to discuss how fluid is made to flow, the characteristics of different types of fluid flow, and viscosity, a property of fluid that can affect fluid flow and its measurement. We'll begin with what makes fluid flow. Fluids are caused to move by pressure. Now, there are several different types of pressure that you may be familiar with or will hear about as you study fluid flow and flow measurement. However, in this program, we're going to concentrate on static pressure, dynamic pressure, and differential pressure. Static pressure is the pressure exerted by fluids at rest. For example, the liquid in this tank is exerting static pressure against the walls of the tank. As we'll see later in the program, static pressure is important in the measurement of fluid flow. Dynamic pressure is the pressure or force above static pressure that completely transforms the kinetic energy of fluid into potential energy. In other words, dynamic pressure is pressure above static pressure caused by the movement of fluids. Dynamic pressure can be produced mechanically, commonly by use of a pump, or it can be produced by gravity, as in this water tank. Differential pressure is the pressure difference between two related pressures. The key here is related pressures. You may observe a difference in pressure in many places and on many occasions. However, unless they are related pressures, the difference is not differential pressure. We will see how differential pressure can be used to determine fluid flow rate later in this program. An important consideration when measuring flow is the flow profile of the fluid. As fluid flows through a pipe or container, its flow can be very smooth or it can be very turbulent. Smooth flow is called laminar. With laminar flow, the fluid particles move along essentially parallel paths, and the flow is smooth and undisturbed. Turbulent flow, on the other hand, is agitated and disturbed. The flow may appear to have small, high-frequency fluctuations or eddies. Flow can also be somewhere between laminar and turbulent. This flow is called transitional and must be considered if the flow you're measuring has the characteristic of changing from one type of flow to another. Now that we have discussed what makes fluid flow and how it can flow in a pipe or container, let's look at the property of fluid that can contribute to laminar or turbulent flow characteristics: viscosity. Viscosity can be defined simply as a measure of how freely a fluid flows. All we have to do is look at some different liquids, such as oil and water, to realize that liquids have varying degrees of viscosity. Viscosity results from internal friction between particles of the liquid. The physics of viscosity are complex, but for our purposes, we only need to consider the effects of viscosity on the measurement of fluid flow. One very important characteristic of viscosity is that it usually is affected by temperature changes. The viscosity of a liquid generally has an inverse relationship to its temperature. The higher the temperature, the lower the viscosity. A good example of a highly viscous substance is molasses. As its temperature rises, its viscosity decreases and it flows more freely. When a fluid travels through a pipe, its internal friction and the friction between the surface of the fluid and the walls of the pipe resist the movement of the fluid through the pipe. This friction or resistance to flow depends on the viscosity of the fluid in the pipe. The viscosity can also determine whether the flow is internally turbulent or laminar, that is, whether the molecules of the liquid slide easily across one another or do so with difficulty. If the flow is laminar, There will be less frictional resistance at the center of the flow, where the molecules are sliding against each other, than at the pipe walls, where friction occurs between the liquid and the pipe surface. Because flow is often measured in terms of velocity, you can see how a situation like this, in which different portions of the flow are moving at different velocities, could affect the measurement. In any given situation, the flow profile, whether laminar, turbulent, or transitional, will depend in part on the viscous forces that resist flow, and also on the forces that act to keep that flow moving at a constant rate. The relationship between these two forces is called the Reynolds number. This is the ratio of inertial force to viscous force that is specific to the flow conditions. Like specific gravity, the Reynolds number is a dimensionless unit and is not absolute for a given liquid substance, but varies with the conditions of flow. As you'll see when we look at specific methods of flow measurement, the Reynolds number is often a significant factor in how well a device will perform and the applications for which it is suitable. You'll find more information on Reynolds numbers in your text. In this part of the program, we've discussed what makes fluid flow and some of the characteristics of the fluid that will determine if the fluid flow is smooth or agitated or disturbed. In the remainder of the program, we're going to look at the various techniques and instruments that are used to measure fluid flow. Now that we have reviewed some properties of fluid that can affect fluid flow and seen how changes in pressure and temperature affect the volume of fluids, we're ready to discuss how flow can be measured. We'll look at some types of instruments that will measure and indicate flow, but right now let's talk about fluid flow and how it's measured. To begin, it helps to know some of the different approaches and terms that are most often used in flow measurement. One of the most common approaches used in flow measurement is flow rate. This term actually refers to the velocity of flow, or how fast the fluid moves. To measure flow rate, it's necessary to know how far a particle of fluid moves in a given period of time. For example, let's assume that a molecule of fluid in this pipe moves from this point to this point in 1 second. If this distance is 10 feet, then the flow velocity of the fluid in this pipe is 10 feet per second. Feet per second is a fairly common unit for measuring velocity. Later in the program, we'll see some instruments that will measure velocity and indicate the flow rate of the fluid being measured. Another approach used to measure fluid flow is volumetric flow rate. This approach involves measuring the volume of fluid that passes a specific point in a specified period of time. The simplest way to measure volume is to transfer a specific volume of fluid from one container to another and time how long it takes to do it. In this case, we have 2 tanks connected by a pipe with a shutoff valve in it. Now, if we know that this tank contains 100 gallons, we can open the valves and time how long it takes the 100 gallons to be transferred to the other tank. Let's say that it takes 2 minutes. The volume flow rate through this pipe is 100 gallons in 2 minutes. If we divide 100 gallons by 2 minutes, we get a volumetric flow rate in this pipe of 50 gallons per minute. Gallons per minute, or GPM, is a fairly common term used to identify the value of the volume flow rate of liquid in a pipe or system. On the other hand, gases are often measured in cubic feet per minute or hour. Later in the program, we'll look at some instruments that actually measure volume flow rate. Still another approach used to measure flow is mass flow rate. Mass flow rate is the amount of mass that passes a certain point in a specified period of time. Determining mass flow rate involves measuring the weight or mass of the substance flowing through a system. The measurement of mass flow rate is commonly used when the specific mass must be known. For example, the amount of fuel oil that is pumped into a tank can be determined by measuring the weight of the oil as it's pumped into the tank. For example, if 1,000 pounds of fuel oil flows past a point in 1 hour, we would have a mass flow rate of 1,000 pounds per hour. Another common unit used to express the amount of mass flow rate is tons per hour. The value used to express mass flow rate must specify a mass unit, such as pounds or tons in its value. As we discussed earlier, temperature and pressure can affect volume, especially the volume of gases. So when flow is measured in mass flow rate, the temperature and pressure of the fluid must be considered and compensated for. When we discuss mass flow rate measuring instruments later in the program, we'll see how these factors are compensated for, sometimes by the instruments themselves. In the next part of the program, we'll apply many of the principles we've covered so far as we look at one class of flow meters. In this part of the program, we're going to look at an important class of flow measuring devices that's been studied and used for centuries. It's called the head-type differential pressure class of flow meters. Let's review the physical principles that underlie the operation of all meters in this class. When a fluid passes through a constriction, the flow velocity must increase if mass flow rate is to remain constant. To accomplish this, the same volume of fluid will pass by points A and B within the same period of time. But in order to do this when the size of the passage narrows, the fluid must obviously flow at a faster rate. Except for energy lost through friction, which we will not consider here, the total energy of the fluid must remain constant. In the 18th century, this principle of conservation of energy was used by Bernoulli to formulate his equations describing fluid flow. The total energy of a fluid consists of two components, potential energy and kinetic energy. Potential energy corresponds to the static pressure that the fluid exerts upon the walls of the passage. Kinetic energy corresponds to the dynamic pressure of the moving fluid. In other words, energy is not lost, it merely changes form. So the total pressure, called stagnation pressure, always remains constant. Now, let's see how this applies when there's a constriction in the pipe. When the velocity of the fluid increases to pass through the narrower channel, its kinetic energy and dynamic pressure increase proportionately. However, this means that some potential energy has been converted to kinetic energy, so there must also be a corresponding decrease in static pressure. Bernoulli's equations show that the change in static pressure, called the differential pressure, is directly proportional to the square of the velocity or flow rate. A formula derived from a volume flow equation can be used to calculate the flow rate directly from the differential pressure. The fact that differential pressure can be readily and accurately measured by means of a variety of devices makes this principle suitable for practical application to flow measurement. To illustrate the principle, we've been using an incompressible fluid. However, Bernoulli's law applies to both liquids and gases. When measuring gases, though, it's necessary to account for changes in density. A factor must also be included to correct for energy loss from friction. All head-producing differential pressure flow meters work on the principle we've just seen. The primary sensing element constricts the fluid flow to produce additional dynamic pressure, while the secondary element measures the differential pressure. To convert this measured differential pressure to flow rate involves the use of a fairly complex mathematical formula. You'll find a copy of the formula in your textbook. There are a number of primary elements used to produce the differential head. The most common and the simplest is the orifice plate. It is a steel plate with a small hole machined in the plate. It is installed perpendicular to the process flow, creating the head-producing constriction. To sense the differential pressure, taps are installed upstream and downstream of the process. As the fluid flows through the orifice plate, the flow path is much narrower, so the velocity of the fluid increases. Notice that the flow continues to constrict past the downstream edge of the orifice plate surface. The point of narrowest constriction is called the vena contracta. At this point, the fluid is close to its lowest static pressure. So theoretically, the vena contracta is the best location for a downstream tap, since the differential pressure will be greatest. However, the area immediately downstream of the vena contracta is extremely unstable, and location of a tap in this area will adversely affect the accuracy of the meter. When the taps are in the pipe, the downstream tap should be located a distance equal to 8 times the inside diameter of the pipe from the orifice plate. The upstream tap should be located 5 pipe IDs upstream of the orifice plate. These tap locations will provide the correct differential pressure measurement to accurately measure flow rate. In many applications, the pressure taps are installed in orifice flanges instead of being installed in the pipe. These flanges are specifically designed for flow measurement. The taps are located on each side of the orifice plate. The upstream or high side tap is located 1 inch from the orifice plate, and the downstream or low side tap is located 1 inch from the orifice plate. The orifice flange should be installed in the line so that there is at least 8 pipe diameters of straight run on the upstream side of the orifice and 5 pipe diameters downstream. This will reduce any turbulence in the pipe that could affect flow measurement. You'll often hear this arrangement called an orifice run. Orifice plates have several advantages that make them appropriate for a wide range of applications. They are capable of metering either gas, vapor, or liquids with a high degree of accuracy. Since they're capable of being used in systems that contain either gas or liquid, and because the taps may be located in the piping or the flange, there are several different orifice designs. The most common design has a small hole machined in the center and is called the concentric bore. This type is suitable for most clean fluids, but it does have some disadvantages. When a liquid contains solids, these solids can be trapped or dam up at the bottom of the plate. That will change the pressure drop across the orifice and will affect flow measurement. To compensate for this problem, another type of orifice called the eccentric bore plate may be used. In this case, the hole is off-center. An eccentric bore plate can be used for processed liquids that contain some solids. The plate can be positioned with the bore at the bottom of the pipe to allow the solids to pass through the orifice plate. Another orifice plate that can be used when solids are present in the flow is this segmental plate. It can handle thin slurries, but its accuracy is less reliable. Orifice plates are often provided with small vent holes, also called weep holes. The weep hole can be located either at the top or at the bottom of the plate. When used in a gas system that may contain some liquid, the weep hole is located at the bottom. For example, in a steam system, locating the weep hole at the bottom allows condensate to pass. When used in a liquid system that may contain gases, the weep hole is located at the top. Orifice plates require very little maintenance since they have no moving parts. Orifice plates perform best with clean, relatively homogeneous fluids and may not be suited for measuring high viscosity flows. It's important to keep in mind that bore wear will eventually affect measurement accuracy and require replacement of the orifice plate. In addition, weep holes and pressure taps may become clogged, causing inaccurate measurements. When clogging occurs, the orifice plate and pressure taps will have to be removed and cleaned. Other widely used types of head-producing differential pressure flow meters include flow nozzles and venturis, as we see here. Their basic principles of operation are similar to the orifice plate. A venturi consists of a converging conical inlet, a cylindrical throat, and a diverging recovery cone. Unlike orifice plates, venturis are well suited to flows with solid content because the walls and throat are smooth and will not trap and hold the solids. Otherwise, their performance and limitations are comparable to orifice plates. Flow nozzles have a slightly different design. As you can see, a flow nozzle has an elliptical contoured approach and cylindrical throat. Unlike orifice plates, flow nozzles do not present sharp edges that may be subject to erosion, so they are well suited for steam and other high-velocity fluids. And like venturis, flow nozzles can also be used for slurries. Still another type of head-producing element is the elbow tap. Elbow tap flow meters operate on a slightly different but related principle. Centrifugal forces developed by a fluid traveling around an elbow curve create a higher pressure on the outside of the elbow and lower pressure on the inside of the elbow. This type of flow meter has pressure taps installed on opposite sides of the elbow. As with other head-producing devices, the differential pressure measured at the elbow tap is directly proportional to the square of the flow rate. Elbow-type flow meters are generally less accurate than the other flow devices we've been looking at. Their main advantage is very low pressure loss. In fact, if installed in an existing pipe elbow, the effective loss is zero. Elbow tap flow meters can also be used with reversed flow. As we've seen in this part of the program, there are many devices that can be installed in the flow path of a liquid to produce a difference in pressure that can be measured and used to determine flow rate. You'll find more information about these and other types of head-producing differential pressure flow meters in your text. Another important class of flow measuring devices is the magnetic flow meter. The magnetic flow meter is a volumetric metering device. Its operation is based on Faraday's discovery that electrical currents are induced in a conductor that is moved through a magnetic field. Let's look at an illustration to see how this is used in a magnetic flow meter. Faraday's law states that the voltage induced in a conductor is proportional to the width of the conductor, the intensity of the magnetic field, and the velocity of the conductor. With a magnetic flow meter, the flowing process fluid serves as the conductor. Thus, the millivolt output of the flow meter is linearly related to the velocity of the flowing process fluid. The flow meter itself consists of a straight length of pipe with no obstruction, so it does not create any additional pressure drop in the pipe. The induced voltage is in a plane that is perpendicular to both the magnetic field and the motion of the conductor. The process fluid passes through the magnetic field induced by electromagnetic coils or permanent magnets built around the short length of pipe called the metering section. Because a magnetic field is used for induction, the metering section must be made of non-magnetic material. Further, if it is metal, it must have a lining that serves as an electrical insulator for the flowing liquid. In order to serve as a conductor, the flowing fluid must have an electrical conductivity. The voltage induced into the flowing fluid is measured by two electrodes projecting through the metering tube liner. The millivoltage measured by the electrodes is directly proportional to the average flow velocity, and thus to the volumetric flow rate of the liquid passing through the meter. The voltage induced in the fluid as it passes through the magnetic field is picked up by the electrodes and measured. This measuring device can be calibrated to indicate flow rate, volumetric flow rate, or mass flow rate. Two general problems must be dealt with in the application of these devices to flow measurement. One is signal distortion and interference caused by extraneous voltages that are either induced or already present in the system. The other problem is coating of the pickup electrodes by a non-conducting material. Let's talk about these extraneous voltages, which are often referred to as noise. Noise can have a serious effect on measurement accuracy. This is because the voltages induced into the flowing liquid and picked up by the electrodes are so small. The addition of noise will therefore produce an error in measurement. Noise can be corrected by using a reference current from the same source. The circuitry of the voltage measuring device can isolate irregularities in the reference current and filter them from the meter output. Other sources of noise are produced within the meter or the process. The liquid may bear trace voltage, either induced from exposure to a source of electromagnetic interference upstream, or static charge produced by friction as fluid flows. These sources of noise can be partially eliminated by zeroing the instrument with the meter full of non-flowing process liquid. Magnetic flow meters can only be used for measuring flow of conductive liquids. The degree of required conductivity depends upon the design of a particular device and is usually specified by the manufacturer. Because this type of meter does not obstruct the flow path, it can be used with high viscosity liquids or processed liquids containing some solid material. In addition, magnetic flow meters do not create pressure loss. Since they measure velocity directly, variations in density do not affect their accuracy. Also, they have no Reynolds number constraints, so they may be used for measuring the velocity of liquids with any flow profile. Thus, aside from their limitation to conductive liquids, magnetic flow meters can be employed in a wide range of industrial applications. As we said earlier, another problem that can be expected from this type of meter is coating of the electrodes by non-conductive material, either the electrolytic byproducts or clinging process material. This buildup is usually gradual, but its effects can be significant over time. Some magnetic flow meters are available with removable electrodes, which may be inspected periodically and cleaned if necessary without dismantling the meter. Ultrasonic cleaning systems are also available to remove accumulated non-conductive material without opening the system. Because they are accurate, reliable, do not intrude into the system, and can be maintained without shutting down the process, magnetic flow meters are widely used. Since they produce an electrical output, they are compatible with the electric and electronic control systems. This is a popular type of flow measuring device that you'll find in a variety of applications. In some industrial processes, an accurate measurement of mass flow is required. For example, mass flow is typically used to measure natural gas delivered to residential customers. In this part of the program, we'll examine several types of mass flow meters. But first, let's get acquainted with some principles of how mass is measured. Mass is a measure of the quantity of matter in a body and is one of the three fundamental quantities: length, mass, and time. Mass is independent of the physical properties of the matter itself. Mass is also independent of the ambient condition in which it is measured. There are basically two ways that mass flow is measured: with a mass flow meter or with an inferential mass flow meter. A mass flow meter is a flow measuring device in which the reaction of a sensing element is proportional to the mass flow rate. An inferential mass flow meter is a volumetric flow rate measuring device whose output must be converted to mass flow. Mass flow can be calculated from volumetric flow rate or from velocity. However, if variation in density is a characteristic of the process, these measurements will not accurately reflect the true mass flow rate unless there is compensation for density. Let's look at some flow meters used to measure mass flow. The first one we'll look at is called an angular momentum mass flow meter. This type of flow meter has long been one of the more popular approaches to mass flow measurement. The two major components of this meter are the turbine and the upstream impeller. In operation, the impeller is driven at a constant velocity by a small motor. As fluid enters the impeller, it takes on the rotational velocity of the impeller. Upon exiting the impeller, the fluid has an angular velocity equal to that of the impeller. The fluid then confronts the turbine, which rotates about the same axis as the impeller. However, the turbine is constrained from rotating by a calibrated spring or by some other restraining force. The fluid has assumed the angular motion of the impeller. This angular momentum in the fluid is transferred to the turbine. The torque produced in the turbine is directly proportional to mass flow. Now, let's look at another type of mass flow meter that produces a different, though related, force as a means of measuring mass flow. It's called the Coriolis flow meter. Before we look at the design and operation of this device, let's review the physical principle its operation is based on: the Coriolis force. If a person standing at the center of a rotating platform attempts to walk radially toward the outside, he will experience a force acting in the plane of rotation and tangential to it. In other words, the force will tend to push the person to the side. This is called the Coriolis force. It is this force, produced by the rotation of the Earth, that makes water in a vortex swirl clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. The Coriolis force produces an acceleration when it acts upon a mass. A measurement of the force or torque exerted by the Coriolis acceleration provides the means for direct determination of mass flow. This is because torque is equal to mass multiplied by acceleration. This illustration shows one type of Coriolis mass flow meter. It consists of an impeller with radial vanes positioned so that the vanes are in line with the direction of flow. A small motor turns the impeller at a constant rate. The vanes guide the flow in a direction that is radial and perpendicular to the axis of rotation. As in the case of the person on the revolving platform, this produces a Coriolis acceleration, which in turn exerts a force on the vanes. A force sensing device measures the torque produced by the Coriolis acceleration. The amount of torque is directly proportional to the mass flow rate and can be used to calculate the flow rate directly. This device has a quick response time, so it is especially applicable for processes with rapidly changing flow rates. Another type of Coriolis mass flow meter has a U-tube design. Let's look at an illustration to get a better idea of how it works and measures flow. This Coriolis mass flow meter consists of a U-shaped tube. Process fluid flows through this tube. As it does, an oscillator vibrates the tube rapidly along the axis formed by its open ends. The resulting angular motion is equivalent to the rotating platform we saw a moment ago, and the flowing process fluid is equivalent to the person attempting to walk toward the edge. The result is that a Coriolis acceleration is induced in the flow, tangential to the axis of rotation and perpendicular to the flow path. However, because the angular motion is oscillatory, the direction of the acceleration alternates. The accelerated flow exerts a force on the walls of the tube. Since fluid is flowing in opposite directions in the two arms of the tube, the direction of the force at any moment will be exerted in opposite directions, upward on one arm, downward on the other. These forces produce a twisting motion in the tube. The amount of deflection is detected by an optical or magnetic sensing device and is proportional to the mass flow rate. The tube has no moving parts in the process stream and offers no obstruction to the flow path. This type of flow meter may be used for low to medium viscosity liquids and slurries. It may also be used for mass flow measurement of gases if the density is sufficient to generate the force necessary to produce a measurable deflection in the tube. We've seen only a few of the mass flow meters that you'll encounter as you work in this field. You'll also find material on additional types of mass flow meters in your textbook. In this segment, we're going to look at a mechanical instrument that measures flow rate by measuring the velocity or speed of the fluid flow in a pipe. We'll also look at a type of instrument that transfers a specific volume of fluid from its input to its output and counts the volume each time it transfers the fluid. Let's begin with the meter that measures the velocity of fluid flow to determine flow rate, a current type flow meter. In this case, we're referring to fluid current, not electrical current. Current type flow meters infer flow rate by the reaction of the fluid on a propeller or turbine. Current type flow meters that are installed in a pipeline are called turbine flow meters, and that's the type we'll look at. A turbine flow meter measures the velocity of flow by translating the linear motion of the fluid into rotational motion. Most turbine flow meter designs incorporate a meter housing with end fittings for connection to a pipeline. A turbine-like rotor is mounted in the housing. The flow rate signal can be recorded using a counter, or an electrical signal may be taken from the turning rotor blades. Most turbine flow meters have straightening vanes upstream of the rotor to ensure the fluid enters the rotor free of swirls. Rotor designs vary from one model of axial turbine flow meter to another, but the rotor generally has a hub from which the flow vanes project. The hub rotates on sealed bearings. Whether the rotor is linked to a counter that counts its rotations or is connected to an electrical device, the actual flow rate is determined from the number of rotations of the rotor per unit of time. Turbine flow meters used for gas service are characterized by a large central hub that is used to create a Venturi effect by decreasing the area in the pipe. This increases the velocity of the gas, providing it with greater momentum to ensure that it will produce enough torque to drive the rotor. In addition, a minimum velocity is required to drive the rotor. This constraint varies with the density of the process fluid. A heavier fluid has greater momentum than a lighter fluid. Turbine flow meters are capable of a high degree of accuracy when calibrated and installed correctly. However, the moving parts, especially the rotor bearings, are subject to wear that will eventually affect measurement accuracy. Now, let's look at a type of flow meter that measures fluid flow by transferring a specific volume of fluid from its input to its output and counts each volume. These instruments are called positive displacement flow meters. Now, there are several different designs, but they all measure flow by counting the number of specific volumes of fluid they transfer. One of the earlier and more common positive displacement flow meters is the nutating disc. This type of instrument is frequently used to measure amounts of fluid delivered. A common application is a water meter for residences or businesses. Let's take a look at an illustration of the nutating disc flow meter to see how it measures flow. The meter consists of a housing that contains the nutating disc. The inlet and the outlet of the housing is usually marked. A counter drive pin is attached to the center of the disc. The meter is connected in the system so that the fluid enters here at the inlet. The fluid fills this space and causes the disc to turn. The disc continues to turn until the outlet of the meter is opened. This specific volume of fluid is discharged into the system. Now, as the disc turns to transfer the specific volume of fluid from the inlet to the outlet, the counter drive pin moves the counter to keep track of the volume of fluid that is passed through the meter. Nutating disc flow meters are designed for relatively small pipe sizes and are generally limited to flow rates of 150 gallons per minute or less. Another frequently used positive displacement flow meter is the lobed impeller type flow meter. In this type of positive displacement flow meter, two lobed impellers are gear synchronized to rotate in a proper relationship. The fluid enters the inlet of the meter and causes the two impellers to turn. These two impellers rotate in opposite directions. As the impellers rotate, measuring chambers are formed. The fluid is trapped and moves to the outlet of the flow meter. Each chamber formed by the rotating impeller holds a specific volume of fluid. A counter is usually attached to one of the impeller shafts to count the specific volumes of fluid that pass through the flow meter. A variation of the lobed impeller flow meter is the oval gear flow meter. As you can see from this illustration, they look very much alike. Their principle of operation is exactly the same. However, they are designed somewhat differently. Instead of lobed impellers, there are two oval gears that mesh together and turn as fluid flows through the meter. A counter is usually attached to one of the oval gear shafts that counts the number of specific volumes of fluid transferred from the inlet to the outlet of the meter. The other types of positive displacement flow meters are constructed differently, but they all operate on the principle we've seen. They admit a specific volume of fluid at the inlet, trap the fluid, transfer the fluid to the outlet, and count each volume as it passes through the meter. Fluid flow may also be measured by installing an obstruction in the flow path in such a way as to produce eddies or vortices in the fluid. One type of instrument that is designed to produce these vortices and measure flow by measuring the effects produced by the vortices is the vortex shedding meter. Let's look at an illustration of an obstruction installed in a fluid flow path and see how vortices are formed. Vortex shedding is produced by the use of a blunt, flat-faced body called a bluff body that is placed in the fluid flow so that it's perpendicular to the flowing fluid. The bluff body is positioned in the middle of the flow path with sufficient space for the fluid to pass around it. As fluid passes the bluff body, the sharp corners cause a fixed point of fluid separation that forms a shear layer. In the shear layer, high velocity gradients exist, and the fluid within the layer is unstable. After some length of travel past the obstruction, well-formed vortices occur in the fluid. The frequency of these vortices is linearly proportional to the fluid velocity. This phenomena has been known for years, but only recently has it been used to detect and measure fluid flow. Vortex shedding flow meters are generally comprised of three basic parts. They are a vortex generating element, in this case a bluff body, a sensor to sense the frequency of the vortices and produce a signal that can be measured, and finally, a transmitter to amplify and condition the signal. The passage of the vortices is usually sensed in two ways. They are sensed by detecting and measuring the fluctuating pressure in the wake of the bluff body, or by detecting and measuring changes in local velocity fluctuations around the bluff body. Vortex shedding meters are fairly accurate in higher velocity liquids or gases. However, in lower velocity fluids or in liquids with high viscosity, accuracy decreases. Another type of vortex detecting and measuring instrument is the vortex precession flow meter. In this type of flow meter, the fluid is forced into a swirl condition by guide vanes that are sometimes called swirl blades. As the fluid exits the swirl blades, it is contracted and then expanded in a venturi-like passage. The center of the swirl becomes displaced from the meter center line. The center of the swirl follows a helical path as it proceeds downstream through the enlargement. This helical path causes fluctuations in the pressure and velocity of the fluid. A sensor can be placed downstream of the guide vanes to detect and measure the frequency of the swirling precessions. This frequency is linearly proportional to flow rate. The vortex precession flow meter has an overall accuracy and range comparable to the vortex shedding flow meter. However, it does have one major disadvantage. The pressure loss that occurs when using the vortex precession flow meter is about 5 times greater than with the vortex shedder. As we've seen in this program, there are many factors that must be considered and compensated for to accurately measure fluid flow. We have also seen that there are many different methods and instruments designed to accurately measure fluid flow. The types of flow meters used in your facility, whether head-producing, magnetic, mass, positive displacement, turbine, or others, will depend in part on the process characteristics and the degree of measurement accuracy required. The information in this program has been general in